Check 1, 2, 3. Okay, hello guys. So this is going to be the recording of our lesson on the topic of the first chapter, the states of matter. This is our objective for today. We're going to have 6 objectives that we're going to cover in this meeting. The first topic is about the distinguishing properties of solids, liquids, and gases. Okay. Let's go for this one here. So before we go further here, let's understand the meaning of the states of matter. Okay. Now, let's go into the meaning of matter first. What is matter? In science, matter is meant as something that has mass and occupies space. Okay. Anything that fulfills these two is considered to be a matter. Okay. Now, we can find ourselves what are the example that is non-matters. Example of the non-matters, for example, will be energy or force. Okay. There are still a lot of physical quantities that is considered to be non-matter. Okay, now after getting the idea of matter, now let's go into the concept of states. Okay. There are several English meaning of the word states. The one that we are going to cover here, states is the condition, or okay, in the modern terms we call them phase of matter. Okay. Now, taken together, states of matter means the distinct forms in which that a matter can exist. Okay. What are the forms that matter can exist? Okay. Now, there are 3 main states of matter that we are going to discuss in the IGCSE level. They are the solid, liquid, and gas. By far, this is not the only state of matter in the world. There are many more. If you care to search yourself, you can find that are more than 10 types of states of matters. Okay. Now, in this case here, our first objective is able to state the distinguishing properties. Properties that let us distinguish, makes difference between one another. Or that is how do we identify. The properties to distinguish are properties that let us identify which state of matter a matter is in. 2 things that we're going to use here is the ability to change shape and volume. Now, in this case here, we can define solid as something that has fixed shapes and also fixed volume. Okay. Because the shape is fixed, they cannot flow. We call them non-fluid or not a fluid. Because the volume is fixed, we cannot make them bigger or smaller. We say that they are non-compressible. Okay. Next, how do we understand that something is a liquid? Liquid is able to be distinguished from the shape that can change. It can change the shape going to the form of the container it has. We call these conditions fluid, ability to flow. Fluid is anything that is not solid. Okay. But something that is similar between liquid and solid is that the volume is fixed. Okay. The shape of liquid may change according to the container, but the volume is not. If you have 1 liter of water, it's still 1 liter, whether you put them in a bottle, you put them in a bucket, or you put them in any other container. Okay. So, a liquid is something that is fluid, but not compressible. Okay. And the third one is a gas. This has the one thing in common with liquid, in that it has no fixed shape, it is fluid, but something that is distinguishing it from the other, solid and liquid, is it doesn't have any fixed volume. Okay. It is going to fill any volume that it is put into. We call this being compressible. We can expand a gas, we can compress a gas, they're going to fulfill whatever space available into it. Actually, there is the higher level of gas, we call them plasma. Plasma is a gas that has been ionized. Okay, later about them here. Okay, so here we're going to put them side by side, solid, liquid, and gas. Okay. Now, as you can see here, okay, why they behave the way they are about the rigidity of shape and volume is determined by the way their particles are arranged. Okay. Solid here, they have fixed volume that cannot be squashed here. They have rigid. Okay. Why? We're going to see later on. It's about how the particles are arranged. Okay. Okay, now the arrangement of particle in solid is the solid is arranged in a particular condition. They have a pattern here. In 3 dimensions, the pattern in 3 dimensions, we call them lattice. Now, the thing is, the particle of solid, liquid, and gas, all of them is actually keep on moving. I repeat, all the particles of solid, liquid, and gas, they are all moving. What is different is the degree of movement. In particle of solids, the particle can only vibrate. Vibration is movement, okay, along a particular position. So they do have more or less a fixed position here. They can only move about that way. They are strongly attached from one another, such that if you're going to pick one particle, everything is going to be tagged along. This explains why solid is non-compressible. There is simply no space for us to compress them. There is no space for the particle to get into. And also why they are rigid. It's because the bond between them is so strong and permanent. If you take one of them, everything goes along. And this is the representation of liquid. In a liquid, the particle, they are always touching each other. Okay. They are free to move, okay, but they are not enough to, let's say, to fly. Okay. They are not enough to fly above here. They keep being in contact with one another. Okay. And this is also the reason why they are practically non-compressible. Okay. They change the position here, but there are no space for them to be squeezed into. Okay. And okay, this is the reason why they are going to fulfill any space available for them. Not any space, any shape available for them. Okay. And this is the representation of the gas particle. Gas particle, they simply don't have contact with one another. They behave as individual and they keep on moving. There are a lot of space between the gas particles. The representation here is an exaggeration. The distance between particles in reality is many, many times. Okay, many times the diameter of the particle itself. By many times, we're talking about numbers like in thousands and even million times of the particle themselves. Hence, the gas is going to quickly fill in any available space of them. Okay. Now, those are the representation of the 3 states of matter. Now, after getting here, after getting the idea of their arrangement, we can get the description of separations, arrangement, and motion. The arrangement of the solid, they are going to be close together in a regular pattern. They are going to be stay along with their neighbors, okay? And they will be in a, you will see there are pattern on them. Not all of them like a rectangle, there are other pattern available, but there will be pattern in solid. Now, in liquid, they are close together, okay, but they are random. As if you just simply put several balls here, then you jumble together. But all the balls is going to be in contact with other particles. Now, of the gas here, it's different. The particles far apart, they are random, just liquid, okay, but they are far apart. All the particles able to move. Okay. The movement of the solid is just vibrating on the spot here. Okay, liquid, they're able to move around, and the gas, they're going to move quickly. That's the diagram here. Again, this is about solid, liquid, and gas. Okay, distinguishing properties of them. Okay. Next, we are going to talk about the change of state. The state of matter is not something that is immutable. We can change them. Okay? The change of state is affected by the heat. Okay? Here, we're going to see what we call the phase change diagram. Remember, phase is the modern name of the state of matter. Up until the A level, we're going to call them state of matter. But as you go into the university, the usual term we're going to have is going to be phase. Okay. Now, here it is. Temperature and heat energy is going to be closely related. When particle doesn't have any heat energy, as we recall in the checkpoint, heat energy is energy that lets particle move. Okay. Without heat energy, particle practically is not going to move here, they're going to be solid. Okay. Now, if we give solids heat energy, the particle is going to vibrate, they're going to move. They are going to move faster and faster the more heat energy you give them. So we're going to be able, we will be able to detect them because their temperature is going to increase. The temperature increasing, they will have an endpoint. Okay. There will be a highest possible temperature in which a substance is solid. At this point here, what happened is the particle cannot stay in their formation. Any heat energy available at this point, they are going to vibrate so much they break their bonds. So at this point here, at this temperature, any extra heat energy we give to particle, they are not going to be used to increase the kinetic energy. Instead, the energy is going to break the solid. So the particle is now still in a group, but no longer having a rigid bond. The effect is changed from the solid to the liquid. In the process here, the solid cannot increase the temperature as long as there is still bond there. So the temperature is not going to change until everything melts. In this case here, any heat energy we give them, we cannot detect them. The temperature not change. This is what we call the melting point. The melting point is the temperature at which the state of matter happens. During the melting point, any energy given to substance is used to break bonds, not to make the particle move stronger, move faster. Only if all the particle has broken the bonds in the solid, totally became liquid, that any extra energy we give them is going to make the particle move faster. And that's the end of the phase change. The end of melting happens when all solids turns into liquid. When everything is not liquid, no longer solid at all, any extra energy we give to them is going to be absorbed by the particle, used to make them move faster. So temperature increase again. Liquid is going to slide faster and faster and faster. They're going to increase temperature. Again, we are going to hit a second limit. In this second limit here, the liquid has slides along one another here at the fastest possible way. At this point, if you still give them heat energy, the energy is not used to make the particle move faster. What happens is they are going to use them to break the bonds between the liquid particle. So the particle become individual. Okay. They change into gas. Why the gas and the liquid has the same temperature during the phase change? It's because they move with the same speed. They have the same kinetic energy, hence the temperature is the same, but they are in different bonding condition. Liquid, they are bonded to one another. Gas, they are free. But still, they are in the same kinetic energy level, hence the same speed of particle movement. Okay. Just like the melting, as long as there is still a little bit of liquid left, any energy is going to be absorbed by the liquid used to break the bonds, change into gas. During the condition here, the temperature, if you put a thermometer, will not change at all. Only if everything that is liquid vaporized, change into gas, then the gas particles itself, they can move faster. In this case, any extra energy we give them, they're going to be absorbed by the gas used to make the particle move faster. Until, of course, they're going to hit the next level, okay, when they change into the fourth set of matter, the plasma. But that is discussion for another time. So in this case here, it is important to understand heat is going to be absorbed by the particle. Okay, but there are two ways they are going to absorb heat energy. One way is to make the particle move faster. Be solid, liquid, and gas. If we give them heat, they are going to move the particle faster, hence temperature increase. But for solid and liquid, there is a maximum temperature that the particles can move in that condition. When that condition is reached, any heat energy given is not going to use to make the particle faster, but to break the bonds between the particles, okay, and they're going to change the state of matter. This is what we call a heating curve. Heating curves tell us, okay, what happened when we give heat to a substance, the effect of heat to the temperature. The key point, we will have two horizontal lines when there is a change of matter. And that is about the phase change diagram, the effect of temperature on a pure substance. Why is the keyword pure here? Different substances has different melting and boiling point. In fact, melting and boiling point is used to identify substances. No two substances has identical both melting and boiling point. So of course, if you have a mixture of substances, we're going to have a different condition. Later on the topic of purity. Okay, so after this, we're going to talk about the next topic. And this chapter is about the kinetic particle theory. The kinetic particle theory is the one who's going to explain this curve. It starts with simple idea here. There are two parts of the theory, the particle part and the kinetic part. The particle theory says that all matters consist of small items. Okay, we call this particle. This is the particle part. Okay, there are three types of particles here: atoms, molecules, and ions. Later about them here. Okay, we call the particle if it still has the properties of the matter. So properties of water, for example, there is a particle of water that behaves like the water we know. We call them molecule of water. For the diffusion of the particle, we'll make them lose them here. We know that the water molecule consists of hydrogen and oxygen atoms. We break the molecule, we break the particle, the properties change. There are three types of particles here: atom, molecules, and ions. Now, these particles, they are always in constant random motion. Okay. This is the kinetic part of the theory. The keyword random means it's not predictable. There is no directions of magnitude that we can know of. But the average of them, we know. Individual particle, we cannot predict. But as a group, as a population, we do able to predict, especially the direction, which is generally going to be equidistant. Okay, in three directions going to be equal, and the magnitude that is going to increase as the temperature. Now, the theory, kinetic particle theory, in short, says that the state of matter, they are different because of the degree of movement of particle. Solid, they can only vibrate. Liquid, they can slide. And gas, they are free to move. Okay. Now, this is the extended particle theory. You can read them themselves here. This is going to increase. This is going to explain the items that we've discussed previously. Okay. In this case, there is a new concept of the intermolecular forces. Okay, that will be it for today. Okay, we're going to continue next time. Okay. Let's have what we have done here. So we have discussed about the state, the distinguishing properties of the solid liquids and gases. This is in terms of ability to change or inability to change the shape and volume. The structures here, okay, we need to know about the separation, arrangements, and motion. Okay. Next, we have discussed about change state of matters in terms of later here. We haven't discussed them here. Okay, there are several types, several change of matter possible here. Okay. We have discussed next here is about the state of matter in terms of kinetic particle theory. The interpretations of the heating curves. The cooling curves is the opposite of the heating curves. Okay. That will be it for today. Thank you very much.